So welcome to the second experiment. The first one, the aims of the experiments is actually to determine the spring constant using harmonic oscillations of a mass spring system. So in these experiments, you're gonna use the springs and mass system. The spring concept. So the spring concept of the mass spring system is about the Hooke's law. When you have the spring and the mass, then you have displacement of the object. So here, let's say delta x. So there's a repulsive force to push or to pull the object back to the equilibrium. So the basic equation is F equal to minus k delta x. As well as, because we are talking about the something moving back and forth periodically, so we are going to have the periodic. The periods of the motions could be the solution of the second order of the differential equations. So it's gonna be t equal to 2 pi square root of m, the mass you're swinging on the oscillatory systems, divided by the spring constants. That's why we need to determine spring constants here. Or if you took the square of the period, so then you will get square of period equals to 4 square of pi divided by k, and the total of mass, which is mass of your object, and then mass of the containers, and then F times mass of the spring. So F here I put in the red color, highlighted with the red color, means you need to take into account what kind of F here. So the determining of the F value for the linear regressions will be very beneficial for all of you to determine and evaluate what kind of the oscillatory motion will be and what does it mean. So you need to discover what F here and what the consequence of your F. F could be between 0 and 1. So it could be 0.5, it could be 0.7, it could be 0, or it could be 1. So it's just ranging from 0 to 1. Materials and tools in this experiment. So you will have the spring, a couple of coils of the metals, then balance scales, and then the third one is the masses and the containers. So your mass is like a coin masses, and then it could be fit on the containers here, like a pipes here. And then the fourth one is going to be the static and rulers. The static to hold up the system into the vertically, so it can freely oscillate very well. And then the last one, you need to record the times, which is the period. The video here is going to show you how to measure the mass of your spring. And similarly, we need to determine the mass of the containers. So, once you have done with the measurement of your mass in the total ones, which is the mass of your coin masses, and then the containers, and you measured your spring mass, and then you oscillate for whatever 10, 20, 30, 40, 50 or hundreds oscillations, and then you take tens of the oscillations, then take the average, and you can fill up all of these tables here, so you get the data. You're ready for the calculations, how to determine the oscillatory systems on the spring mass system here on these experiments. This is the three things you need to provide on your report. So first of all, you need to plot the curve of the forces as a function of delta x. Provide the graph as the relationship between the force and the position of the needle when you add the mass. Then you need to determine the linear regression of the graph. The second one, you need to graph another things, which is the square of the period as a function of the mass. The third one, you need to do some comparisons between the first and the second spring constants you got. What can you say? What is the exact values of your the spring constant? Which one is the proper or the close one to the exact values? Okay, and then you need to explain why this is better than the others. Okay, so this is the first experiment. Let's go to the second part. The experiments about how to determine the gravitation constants. The aim is kind of to determine the gravitation constants using harmonic oscillations of a borda pendulum, or we call it as a mathematical pendulum. Let's talk about the basic concept of mathematical pendulums. So the first one, you need to start with the equation motions. Okay, I is kind of the inertia, and then d square of theta per dt square, which is kind of the acceleration. In this case is the angular accelerations, and then on the right hand side here is just kind of what is the force you have here, which is mass times the gravity or weight. So by solving this equation, you will end up with the third line here, which is d square of theta per dt square equals to minus the omega square of the theta. So kind of the oscillations system. In this case, you need to define why sinus theta could be approaching similar as or equals as theta here. Okay, omega here is actually as a function of the period. T, the period here, is kind of 2 pi times the inertia moments of your object divided by mgh, which is mass gravitational, and the length of the swinging. Inertia moments is m sine 1 plus gamma square plus m2 per 5 gamma square. You can derive from the inertia moments by doing the Steiner's theorems. Okay, you will see the Steiner's theorems, or we call it as the parallel axis theorems. So then your gravitational constant formula is going to be 4 pi square per square of t plus something 2 plus gamma square plus and so on and so on. And then materials and tools of the gravitational constants using the borda pendulum experiments are: the first one static and the borda pendulum itself, the second one protractor to measure the angles you swinging the strings, and then metal sphere objects, ideally it should be completely spherical, and then vernier caliper to measure your diameter of a metal sphere object, then stopwatch to record the time swinging, as well as the rulers here to measure the length of your swing or the string. Okay, this is how you measure the length of the string from the axle you swing the systems until the surface of the spherical object. The next ones, we are ready for the measurements of the metal sphere object radius or diameter here. Okay. And then this video here is to show you how to swing and measure the swinging time. So you use the protractors and then give it some displacement and release. Then the system will be oscillating or swinging in the simple harmonic oscillations. And then you measure the swing by the stopwatch. Here's the data. You need to record from the first ones. You measured hundreds of the swings. This is the data you already manipulated using this table, right? So if you look through the left hand side here, you're gonna use the first, the 10th, the 20th, the 30th, 40th until the 90th. And then on the right hand side here, the number of periods is gonna be 100th, 110th, 120th, and so on until 119th. So if you take the difference between the times or number of periods of hundreds and zeros, means you actually have the 100 times of your periods, because it's not easy to measure 1 times of your period, one single swing. Okay, so you need to measure 100 of swings. But you are not doing 100 of swings and then start from 0, 100 and swing again. No, you just swing from the first ones, the first swing, second swing, and keep going on until 190. So every 10 swings you need to record the times. So from the left and the right, you just take the difference of any 100 times of period. So from the right hand side here, you will have the tenth of 100 period. So you could do take the average of hundreds of period. So you will see the average of your period after you divide it by 100. All right. And then for your report, what is the task on it? First one, you need to determine the gravitational constant using the following equations, which is the gravitational constants plus something on the modification of your length of the swing. Okay, the length of the swing is not this the length of your string only. Okay, that's not enough, because we need to take into account the Steiner theorems. Okay, so use these equations, and then you need to express what you could say of the factors affecting to your results. So for example, your gravitation constant is not very good. What kind of the errors, what's it affecting to your results? So explore, and then you put everything on your report here, kind of the depth evaluation or analysis. All right. And then what I'm going to say, thank you for watching and listening. Good luck for your reports and analysis, and also have a nice day. Thank you.